market, it was like, that's not any variable star that we know, right? And then they zoomed in on it with a Hubble telescope as soon as they got up. Let's take a look at what's going on there. Look at that. Kaboom. That's a star with indigestion, right? Every time it gets all its mass together, it blows itself apart, right? Like, we all know people like that, right? Don't tease them. Now, here's the weird thing is that a normal star, like the sun, okay, is going to be making helium. Helium is a denser nucleus. Don't think like helium atom, like helium gas floats up or something like this, right? Think like helium as in just 4 nucleons all bound together, right? That's going to be more dense than protons running around, right? So helium is more dense, where it's going to accumulate in the core of the star. So this is key concept number 2. The products of whatever you are fusing, the products of whatever you're fusing now, accumulate in the core of the star because they're more dense. Yes? Does this make sense? Now, the star, if it's fusing hydrogen, is not hot enough to fuse helium. Helium takes a higher temperature and a higher pressure. So this stuff's just sitting there and it's not fusing. Yeah? But it's occupying the best place for fusion. So fusion is not happening inside of this core. Where is it happening? Just on the outside of it is the prime space now. Yeah? The best real estate for hydrogen fusion is on the outside of this core. What happens is that core gets bigger and bigger. What's happening to the pressure and temperature on the outside of this? It's going down, isn't it? Because the closer you get to the surface of the star, the less the pressure is, right? So what's going to happen to your nuclear fusion? It's going to slow down, isn't it? It's going to slow down. This is what makes your by the way, it's going to make your red giant. Okay, so this thing is going to slow down because why? Well, because that damn helium is occupying all the good place for hydrogen fusion. Yeah, so it expands, it expands, it expands. The star cools down. Why is that bad for a star? Stars can cool down, but does gravity cool down? Gravity just gravities, right? It's just going to gravity, right? So if you cool a star down, it's going to collapse. This thing's going to collapse, right? So helium accumulates, it displaces that, the star cools. When it cools, heat no longer balances gravity, and it's got this little moment like Wile E. Coyote runs off the cliff and goes, uh-oh, phew, right? I'm just kidding, right? As soon as it cools down, the star goes, uh-oh, right? Okay, now you're going to collapse the helium core. When you do that, okay, when you collapse it, it's going to collapse a lot. It's going to go from huge to like the size of a planet or something like that, right? Okay, so when it does that, this is, by the way, how we exploded the bomb. Totally different process. This was a fission process, right? We made a sphere of uranium and we imploded that. As a sphere, it couldn't explode, but as a solid sphere, it could. Right? So if you collapse this thing, this is how you could make a hydrogen bomb. We have never done it this way, I don't think. Right? Okay? But you implode this thing, and let's just go back to that slide, right? This is hydrogen that is almost fusing, yes? All the way outside here. This is helium. If you collapse this thing, all that hydrogen is going to go, what's it going to do? The star is just going to go and puff up. Yeah? It happens relatively fast. Right? Not like, one day, the next day, but over, hundreds and thousands of years, right? The star is going to puff up. Right? The star puffs up. It's now a red giant, right? Okay? It expands to the orbit of Venus or Earth, possibly to like Jupiter, right? And if you start out with 8 solar masses, you're going to have 1 or 2 residual masses left. So this is an enormous puffing up and exploding in loss of matter, right? So on our little HR diagram, here's our main sequence or something like this, right? It's like a kind of a thing, right? What we've done is we've gone like here and we've gone, okay? We've gone out here and we have, this is hot, this is cold, this is bright, this is dim, right? Okay, we've gone this way. We have gotten colder but brighter. How do you get colder and brighter? You become bigger, right? So we were going this way, right? The star expands, it actually cools down, but it gets brighter because it's so darn big, right? So there's the picture. We've left the main sequence, right? We've gone out here, boom, right? And then what happens there? We expand, and then we cool down, don't we? So what's going on here? Here we are getting hotter but dimmer. How do you do that? Are we getting smaller? Yeah, the size is the other variable on here, right? So if we're getting hotter but dimmer, right, then we must be getting smaller. So the thing goes, boom, puffs up, right? Doesn't spend a lot of time here as far as the life of a star, and then it collapses along here, right? Okay, cools down, it expands. And here's an artist's picture of, well, no, okay, somebody just drew this, right? Possibly it could expand all the way to Jupiter, and here's Jupiter, right? And what's interesting is that, of course, the temperature at the center of Jupiter is actually hotter than the surface of the sun, right? You know, so Jupiter could actually like go into the sun quite a ways and still be Jupiter, right? Jupiter's like not nothing, right? It's a chunk of stuff, right? Okay, but there's Jupiter getting eaten up by the sun, a moment of impact. That's amazing. Okay, now what can happen now is once it contracts, it can do helium fusion, right? So that's what's going on here, right? So here is hydrogen fusion stops. Does it stop because there's no hydrogen? Why does it stop? Yeah, not enough pressure. The helium core has gotten so big that it's displaced the hydrogen from the center. There's not enough pressure where the hydrogen is, i.e. not the core, for hydrogen fusion to happen. So hydrogen fusion cools, right? And then the helium core implodes. Right, and now we do this like this. This is helium fusion. Right? Helium is going to make nice things. You know, a sun-like star is going to make things like beryllium and carbon. Right? And then on giant stars, right, also we can do this. These things can, by the way, fuse if you've got enough mass later on to become things like iron ultimately, right? Iron would be nickel and iron are the things, right? Okay. It heats and it contracts, so there it is. Right, it's heating up and contracting. This is helium fusion. It's making carbon, right? Where's that carbon going? Where does that carbon go? If you make carbon, where does it go? It goes into the core. Okay, eventually carbon and carbon-like materials, right, are going to displace the helium from the core. What's going to happen? Yeah, it's going to do the same thing, right? So check this out. This is a big one. This is a big, anytime you move this way is an expansion and a cooling, right? Check this out. Isn't that the same motion? Yeah, pretty rapidly, right? So this is what's going on. Carbon fusion. I think we've seen this before, right? It displaces helium in the core. Heat energy no longer balances gravity. The star says, oh crap, right? Gravity crushes it, okay? Collapses the carbon core. Implosion spurs helium fusion. So now it's helium that's puffing the star up, right? In the same way hydrogen did, right? It cools briefly. And so here it is, right? So it does like this, and then it does right? And now it's doing, if it's got enough mass, now it's doing carbon fusion. And carbon fusion can make things, if it's big enough, things like iron, right? And then basically it just peters out at this point. If your name's Peter, I'm sorry about that. Right? So if at this point you have a mass that's bigger than 0.7 times the mass of the sun, okay, after losing all that material when you became a red giant, right? So you have to be much bigger than the sun at this point, right? You can make all these things, right? You can even make in supergiant stars things like iron and nickel, right? But you can't make anything, stars in their normal life cycle can't make anything heavier than that, because to do so would require energy input, right? They can't do it in their normal life, but they can do it later, right? So nucleosynthesis stops with this because of that whole binding energy thing, right? To make things heavier than that is to store energy, right? So here is the most tightly bound nuclei. That's iron and nickel, right? And what we're doing so far on the main sequence is we go from hydrogen to helium. That's the biggest release of energy, isn't it? Yeah? So that lasts the longest. We spend the longest time on the main sequence, right? And then when we go from hydrogen to there, or helium to there, is that as much energy? No, so the star doesn't last as long, right? It's going to use up this fuel much quicker because the fuel has less energy per unit mass. Does that make sense? So this is why it spends most of its life on the main sequence, because that's most of the energy. It burns the fuel only at the rate it needs to overcome gravity, right? If it's burning it faster than that, it puffs up against gravity, and it's like a stove, right? The stove is set at a certain temperature, and if you cool it down, it burns more fuel, right? So this thing is going to burn the fuel